Welcome back to a new video about LC ladder filter design. This is our example number 1, considering the inverse Chebyshev response. We will discuss how we can design for an inverse Chebyshev response for this LC ladder configuration, and we will see that this is also similar to what we have done with the Chebyshev response, but then slightly different steps. Of course, we will see that in a calculation step by step and also verify these in SPICE simulations. So let's look at our problem. Objective is a design of an inverse Chebyshev response passive filter. It must have an LC ladder configuration. It must be a low pass filter. And we need to use 50 ohm double terminated shunt input circuit. And we have discussed this in the previous videos also, that this is the generalized filter we need to design. And then the normalized source resistor RS and the normalized load resistor RL are both 1 ohm as unity. And the specifications are shown here. The maximum passband ripple must be 1 dB, and the minimum stopband attenuation must be 20 dB. The passband frequency is 1 MHz, and the stopband frequency is 2 MHz. So let's see what we need to do for this specific design. The solution, step 1 is to calculate the filter order n, and we know for that we need specific parameters like the epsilon p and epsilon s. Now epsilon p is related to A max. This is what we also have done in the previous videos for the Butterworth response and the Chebyshev response. We know it is now given as 1, so we can just calculate this, and this is just a simple operation. So 0.5088. Now the epsilon s is related to A minimum, which is 20 in this case. So when you substitute the values here, you get now 9.9499. Now taking this together, we will now determine the filter order n for this inverse Chebyshev filter. That is exact same as for the Chebyshev response design. So the formula is exact same. So you again use the epsilon values and also the fs and fp from the specifications. You substitute them and you will get the 2.7834. And we know that we need an integer order, so we need to round this to n is 3. So we need a third order inverse Chebyshev response filter. Step 2 is to calculate the frequency scaling factor Kf. Now this is not really a calculation, but we need to set to this Kf to a specific value, which is actually the omega s, which is 2 pi times this fs, which is then 2 pi times this 2 MHz, which is then 4 pi times this 10 to the power 6, which is, as said, 2 MHz. And we will need to use this for our calculation of our component values. Step 3 is the calculation of the scaled component values we will now determine. Now for that we need to first go to the table. This is the inverse Chebyshev response filter for a third order, so in a 3. And it is for a normalized low pass filter. So these are the normalized component values, and it is double terminated, and it is normalized to a stop band frequency of 1 radians per second. What this means is actually the following: that what we need to design is the maximum passband ripple and the minimum stop band attenuation. In this case we will get exactly the 20 dB, but we will get less than 1 dB, so it is the maximum. So in this case we design for minimum stop band attenuation exactly, but we will get, since we round this up, so from 2.7834 to 3, we will get less than 1 dB ripple, which is of course fine because that was the maximum allowed passband ripple. So when you now go to the situation for again NS3 and this part here, because the A minimum we wanted was 20, so we need to look at this first row. If you get of course 25, you need to look at this. If you for example have 22, you still look at the 25 because that is the minimum required, so we need to go up. Now this is a circuit for the low pass unscaled, so this is a normalized filter. You can see it is similar to what we have used for the Butterworth and also the Chebyshev. The only difference is actually here the parallel combination of the capacitor and the inductor. In this first case it was just the inductor, now we have also the capacitor. So we have now C1, C2 and C3, so 3 capacitors and 1 inductor. And we have the RS and RL. They are all normalized. What you see here in the table is the C1 is equal to C3, which is actually these two values are exact same. And C2 is the value here, all in farads here, and this is in Henry, so this actually is L2, and this is 1 ohm, this is 1 ohm. That is just a normalized. So we need to then move on to the scaled values, which is then our prime value. So you can see the RS prime, L2 prime, everything is now primed. So we now need to go to the primed value. For that, we need to use the formulas and use this coefficients or parameters for the actual component values. So the C1 prime is C1 over the Km and Kf. Now Km is the gain magnitude scaling factor. So this is the magnitude scaling factor here is 50. So that means we also need to use for Km 50. The Kf is already said as the omega s, which is then 4 pi times 10 to the power 6, which is shown here. And this C1 is the normalized value, which is then 1.17172, which is from here. And we now do the calculation here, you get now 1.865 nanofarads. Now for the C2 prime, you look at this and you actually do the similar calculation. Again, omega a Km and a Kf, and C2 is a different value, so you just do the calculation. You get now 509.4 picofarads or 0.5094 nanofarads. L2 prime is a similar calculation we have also done in the previous videos. Now you use the Km times the L2. L2 is from the table here over the Kf, and then you get now here 9.324 microhenries. C3 is exact same as C1, so the C3 prime is exact same as C1 prime, so it's also the same value. RS prime and also RL prime, they're just 50 because it's 50 times 1, so RL is also 50 ohms. So we get now all the component values, so we have now in total 6 component values here. We have now determined our values for this circuit. So let's collect them. These are the component values here, and this is the table we only need to look at. So this is the part. So the design circuit will be then this. You can see in the first circuit here, this is the normalized values. You can see the RS is 1 ohm, RL is 1 ohm. You see C1 is 1.1717 farads. It's actually just this. Only the accuracy here is actually a little bit less. Again, the same for C3, and also C2 is 0.320 farad. So again, the accuracy is a little bit less here, and L2 is also what's shown here. Now we need to, this is the third order inverse Chebyshev response unscaled LC ladder prototype low pass filter. So just a reference. Now we need to go to the scaled version. So it goes 50 ohm for the RS, 50 ohm for the RL. You see the C1 and the C3 are the exact same as we have determined. And C2 is also shown here, is also what we have, and the L2 is also what we have calculated. So now this circuit, we will use the Vout LPF, which is low pass filter scaled, is the circuit we will use to determine that these specifications are met. So let's see that in the simulation result. This is the magnitude plot from and the body plot. You see the inverse Chebyshev response characteristics. What you see is you don't see a ripple in the passband, you only see the ripple in the stop band. So you see only one ripple, by the way. So you see one notch here, and that is a characteristic of an inverse Chebyshev. It does actually the inverse of what the Chebyshev response should do, which is then a ripple in the passband. Now let's go one by one, and then this is the circuit as we have discussed shortly. And let's go one by one by the of the specifications, and also what we see here. We see the passband gain of minus 6.02 approximately dB, which is the 0.5 because at the DC this capacitor is an open, the inductors are short, so we actually have only 50 over 50 plus 50, which is then 1 over 2 or 0.5 as the gain, which is exactly the minus 6.0206 dB. You can just calculate that using 20 log of 0.5. So that's verified. That's actually shown here. The next specification is the gain at 1 megahertz. Now the gain at 1 megahertz is minus 6.6141 dB. Now we started at minus 6.0206 dB. So we go down, that's actually calculation here, by 0.5935 dB. And that is a ripple or a difference which is less than 1 dB. So that is exactly as we wanted. So you can see that the ripple is always less than the maximum allowed ripple here for the inverse Chebyshev response. So that's shown here. Okay, So it is less than 1 dB as required. Now the next one is the stop band attenuation is 20 dB here, really close to 20 dB, because at 2 megahertz we look at this value, which is minus 26.0225, which is looking at again to the baseline here is going down. We go down by almost 20 dB, a little bit larger. So this is exactly as wanted. So it's also according to specifications. The final one is the cutoff frequency, which is not a specification, but we can calculate that, which is actually shown here, 1.3 megahertz. Again, you go down by 3.01 dB, and you can see that it's happening at 1.3 megahertz. But how do we calculate this cutoff frequency for the inverse Chebyshev response filter? So we can use this formula. Again, you look at the Fs, not the Fp, which is the stop band frequency. You use the cosine hyperbolicus and then our cosine of that hyperbolicus, so the inverse of that one, and then use the epsilon s, which is our value, which is actually n at 3, and also the epsilon s are all shown here, and n is 3. So when you now substitute these values here in this formula, you get now 1.3 megahertz, very close to that value. So again, this is verified, and also all specifications are met. So we have less than 1 dB ripple, we have at least 20 dB attenuation. Our passband frequency and our stop band frequencies are also according to the specifications. And there's a notch here, so extra information here. Another information which is also required is that if I go up with the frequency, the attenuation will never be smaller than this 20 dB, because for example, if I go up, you might say maybe this is less attenuation, which is not. It happens at approximately 4 megahertz, but the attenuation is still minimum 20 dB. So after the stop band frequency of Fs, you still have an attenuation which is 20 dB at least. Alright guys, this is our example number 1 about the inverse Chebyshev response and an LC ladder configuration for the low pass filter. We have discussed how we can design this circuit using this prototype low pass filter, going to the scaled values for the actual design. If you have any questions, comments about this example, please let me know and I will try to answer them as soon as possible. See you next time in another video. Take care.